solving chemical problems. Most of the problems we're going to end up doing basically come down to unit conversions. And a method of solving problems using units as a guide is called dimensional analysis. I learned dimensional analysis as a junior in high school in physics class. And looking back, there's far too many years to look back on, I can say that dimensional analysis was the most useful thing I learned in high school. I have used it over and over and over again, and not just because I'm a chemistry teacher. It's also useful in real life. So dimensional analysis. You need to learn dimensional analysis. Hopefully, many of you already know it, but if you don't, I will work with you until it becomes clear. Once it clicks, you'll say, oh, that's easy. Why couldn't I see that before? Until it clicks, it can be really, really confusing, but keep working at it. Very, very important to include units. I've said that a couple times already today. Units, units, units. Write the units. Units get multiplied, divided, canceled, just like any other algebraic quantity. So if A times A equals A squared, centimeters times centimeters equals centimeters squared. And the units will help you out. If the units don't work out, you've got something wrong. You need to fix it. So I'll try to go through this quickly. A unit equation is a statement of two equivalent quantities. Example, 2.54 centimeters is equal to 1 inch. These are different units of measurement, but they're representing the same length. They're just different ways of stating the same thing. They're equal. A conversion factor is when you take that equivalent statement, that unit equation, and you make it into a fraction. So 2.54 centimeters equals 1 inch. Now, if I divide one side by 1 inch and I divide by the other side by 1 inch, those two quantities are still equal, yes? When you take a mathematical equation and you do the same thing to both sides, it's still equal. What is 1 inch divided by 1 inch? 1. That's equal to 1. The inches cancel out like variables. 1 divided by 1 is 1. So 2.54 centimeters divided by 1 inch is numerically equal to 1. That means that if I take this quantity and I multiply it by something else, it doesn't change the value, because when you multiply by 1, it doesn't change the value. We will be changing units, and so the numbers will change, but the quantity we're talking about doesn't change. So you make a conversion factor from a unit equation by putting one of these on the top and the other on the bottom. I can also turn that upside down. 1 inch over 2.54 centimeters. That is also equal to 1. Everybody okay with that? This isn't voodoo math. Most unit conversion problems take this form. There'll be some information that's given, and then some information that they're asking you for. What do you need to find? And in between will be the conversion factor, or factors. Sometimes there's more than one. So you're going to do this. You start with the given unit, and you're going to set up your conversion factor so the given unit is in the denominator. Like algebra variables, they cancel out, and the desired unit is in the top. So let's just do a real simple example. How many centimeters are in 12 inches? 12 inches is the given information. They're asking how many centimeters. So sometimes I'll write this out. 12 inches, and I'm converting to centimeters. So my equation, I'm going to start with 12 inches. I'm going to multiply by a conversion factor, and I want to end up with centimeters. This unit goes on the bottom. This is what I would call a unit path, or my map of how I'm going to get there. This one's real simple. It's one step. I'm going to go from inches to centimeters. So in the numerators, I'm going to go from inches to centimeters. So I'm going to put centimeters up here, and I'm going to put inches in the bottom, because I want these inches to cancel out. Always put the units in first. It's unit analysis. It's dimensional analysis, because the units guide you. You don't have to remember, well, is you're supposed to divide or am I supposed to multiply? The units are going to tell you what you need to do. So you put the units in first, and now you have to ask yourself, what's the relationship between centimeters and inches? Well, we just talked about it, but I'll write it up here again. 2.54 centimeters is equal to 1 inch. So here I've written the conversion factor with centimeters on the top. So I'm going to take this part of the conversion factor, this side of the equal sign, and put it on top. The number goes with this same unit, 2.54 centimeters, and it's 1 inch on the bottom. It always has to be true that what's on the top is equal to what's on the bottom. Okay? So that's how you set it up. Once you learn the pattern, it becomes very, very simple. And now we just go through and multiply. 12 times 2.54. You can divide by 1 if it makes you happy. And my calculator says 30.48. What about sig figs? We're multiplying here, right? How many significant figures does 12 have? 2. How about 2.54 centimeters equals 1 inch? That one's exact, because they actually redefined the inch to be exactly 2.54 centimeters. And anytime you have, most conversion factors will be one of one unit and then a number with the other. 1 meter equals this, or 1 gallon equals this, right? This one is exact. The other one may or may not be exact. In this situation, it is, and so sometimes you'll see this written with an exactly equal to. So because this one is exact, we can just ignore it. It's got an infinite number of sig figs. It's not going to limit anything. So we started with 2 sig figs. We should end with 2 sig figs. So how should I record that answer? Is that good? That only has 1 sig fig, right? Because there's no decimal point. Trailing 0, no decimal point. Well, we could do this. And technically that's okay. It's a little confusing though. So the best thing there is to put that into scientific notation, 3.0 times 10 to the 1 centimeters. That's the best thing. Any questions? General strategy, identify where you're starting, identify the end point, and figure out a way to get there. You guys at least heard of Dora the Explorer? Nod your head? Yeah? Okay. So Dora's always trying to get somewhere. Very confused little girl. Lost all the time. Who do we call when we don't know which way to go? The map, right? And then the map comes out and says, well, to get from the snowy mountain, well, they're usually going to the snowy mountains, but to get from the grassy plain to the snowy mountains, first we have to go over the bridge, and then we have to go down the crooked path, and then we get to the snowy mountains, right? So we need to know where we are. We're on the grassy, what did I say? I don't even remember where we are. We're on the grassy plain. And we're trying to get to the snowy mountains, and we're trying to figure out how to get there. So you need to know where you are, you need to know where you're going, and then you need to figure out how to get there. Sometimes there's more than one way to get there, and that's okay. Sometimes one way is harder than another. If you get there okay, it's fine, regardless of how you got there. So we want to sort, read the problem all the way through, then pull out the numbers and figure out what's been given to you, figure out what you're trying to find, then strategize. How am I going to get from one place to another? Then solve the problem, write it out. I want to see this times conversion factor with all the units written in and units canceled out. Believe me, it will help you later when we get to some things that are more complicated. Do the math, and then check your answer. Look at that answer and say, is that reasonable? Does that make sense? You know, if you're solving for how many atoms are in 1 gram of carbon, and you come up with 2.9 times 10 to the minus 15 atoms, could you have less than 1 atom? Can you have a fraction of an atom? No, that's like, you know, doing a calculation to see how many people are in the average family, and you come up with 0.01. 0.01 people in the average family. Maybe I did something wrong in my calculation, right? So then you go back, you wrote everything out, now you can find out where you made your mistake. What do we got left here? In the interest of time, I'm going to skip those. Well, we're going to get some practice in lab, but I do want to talk about this real quick, units raised to a power. Sometimes you have to convert squared or cubed units, and so be careful. So this is how you build up those conversion factors. 2.54 centimeters is equal to 1 inch. If we're converting inches squared to centimeters squared, then we need to square both sides, including the number. So we've got 2.54 squared square centimeters is equal to 1 squared square inch. Well, 1 squared is just 1. But it's important that the 2.54 also gets squared. And so it actually is 6.45 square centimeters to 1 square inch. And we'll get some practice with that in lab as well. I'm going to skip those. Density can be used as a conversion factor. So I'm going to do this problem to show you. Okay, so backpackers often use canisters of white gas to fuel a cooking stove's burner. If one canister contains 1.45 liters of white gas and the density is 0.710 grams per cubic centimeter, what's the mass of the fuel in kilograms? So we read the problem. Now we're going to sort. Well, we've been given some numbers. We've got 1.45 liters, and we've got 0.710 grams per cubic centimeter. When these compound units or derived units are typed out, it's a lot easier to use a slash. When you write them out by hand when you're doing a problem, write that fraction vertically so that you realize it's a fraction. So that's the information that's given. What's the question? What's the mass in kilograms? So we're trying to find kilograms. And we're given 2 numbers to start with. We're given a volume in liters and a density in grams per cubic centimeter. This is a simple unit, a single unit. This is a derived unit, something per something. Almost always that's going to be a conversion factor, and this is the number you're starting with. So we're starting with liters, and we're trying to get to kilograms. Do we have a relationship directly between liters and kilograms? No. So I'm going to erase this arrow because we're going to need more than one step. Just like Dora's little adventures often are more than one step. It's not just you go from here straight to the snowy mountains. You have to go over the bridge and around the loops and all this other stuff. Well, they gave us this. So we may need to use that. Gram is a unit of mass, and kilogram is a unit of mass, right? So these two are related. Cubic centimeter is a unit of volume, and liter is a unit of volume. So could we get from liters to cubic centimeters? Yeah, we could. So we could go from liters to cubic centimeters. And then sometimes it's helpful to work from the back end too. Kilograms. If we had grams, could we get to kilograms? Sure we could. So if we had grams in here, And then, do we have a relationship between cubic centimeters and grams? Yeah, we do. It's the density right here. So this one has 3 steps in it. So I've written out my path. We're going to start at 1.45 liters, and then we're going to go to cubic centimeters, and then we're going to go to grams, and then we're going to kilograms. And then, backpack, and they'll all cheer and do a little dance. This is the strategy. This tells you now what to do. That's the hard part, the thinking part. The rest of it is just following a pattern. So I'm going to write down 1.45 liters. For every arrow, I'm going to have a conversion factor. 1, 2, 3. And just like the map has Dora, chant, so we chant liters, cubic centimeters, grams, kilograms. Liters, cubic centimeters, grams, kilograms. What we wrote in the path goes in the numerator here. Liters, cubic centimeters, grams, kilograms. That's going to get us where we want to go. The units in the bottom will be the same as the unit in the previous term because we want to get rid of liters. We get rid of liters by dividing. Those will cancel out. We get rid of cubic centimeters by dividing. Those will cancel out. We get rid of grams by dividing. We do all the units first. Then we fill in the numbers. And you can do them in any order. Let's do this one first. Kilograms to grams. What does kilo mean? Kilo means 10 to the third. So here I have gram and gram. And kilo on top, I'm going to write what it means on the bottom. So 1 kilogram, put a 1 there if you need to, 1 kilogram is equal to 1,000 grams. This one, grams per cubic centimeter. This is where density as a conversion factor comes in. They gave us the density, 0.710 grams per cubic centimeter. That is a conversion factor that is specific to this problem. I put the number on top because the unit gram is on top. You have to keep the number with the unit. You can't say 1 gram per 0.71 cubic centimeters. You can't switch it around like that. And then here, cubic centimeters and liters. Well, 1 milliliter is equal to 1 cubic centimeter. And 1 liter was 1,000 cubic centimeters. Remember the big block full of little squares? So 1 liter is 1,000 centimeters. And so you don't want to lose your brain, lose your mind, and say that 1 cubic centimeter is 1,000 liters. A little box that's 1 centimeter on a side is equal to 1,500 2-liter sodas? Maybe that would be backwards. So we've got this all set up. The best way to approach this is just read through left to right, top to bottom. So 1.45 times 1,000, divide by 1. Times this, divide by that. Times this, divide by that. Obviously, if you're multiplying and dividing by ones on your calculator, it's not going to change anything. But some people need to do that, and that's fine. So 1.45 times 1,000 times 0.71 and divided by 10 to the 3. And we come up with 1.0295. And the unit that's left standing is kilogram. How many significant figures should this answer have? 3. This is a measured quantity. This has 3 sig figs. This density has 3 sig figs. That trailing 0 counts because of the decimal point. This is a metric conversion factor. All conversion factors within the metric system, metric to metric, exact. Within the English system, English to English, exact. So this one's exact, we can ignore it. This one's exact. So 3 and 3, this should be 3, so what do I write? 1.03 kilograms. Any questions? Different example. Oh gosh, this chapter will never end. Order of magnitude estimations. I'm just going to go over this real quick. Sometimes we don't need to do a precise, exhaustive numerical calculation and come up with this really great answer. Sometimes we just need a ballpark answer. And so we can do that as an end result, or to just get a feel for it. Is this even going to be a possible thing to do, or to check if our answer is reasonable? And this just focuses on looking at the exponential part of numbers when they're written in scientific notation and ignoring the rest. So if the decimal part of a number is less than 5, you're just going to drop it for estimation purposes. So, if it's 3.97 times 10 to the 2. For this order of magnitude estimation, this part of the number is less than 5, and so we're going to just call this 10 to the 2. If the decimal point is 5 or more, round up to 10 and rewrite the number. So if we have 9.34 times 10 to the 7, well, the decimal part is greater than 5. So we're going to round that to 10 times 10 to the 7, which rewritten would be 10 to the 8th. And we'll do this with all the numbers that we're multiplying or dividing, and then you just have to deal with powers of 10. Let's do an example real quick. Estimate the number of atoms that a mortal being could have counted in the 14 billion years that the universe has been in existence. Do we need a precise answer for this? No. So, 14 billion years, and what's kind of missing here is, well, how fast are they counting? How many atoms do you think you could count in a second?
Book says 10.
Book says 10. Good, thank you. So, counting 10 per second seems reasonable. 10 atoms per second. So we've got 14 billion years. We've got 1 year is equal to this many seconds, and we've got 10 atoms per second. What are we trying to find? What's the question? Estimate number of atoms. So number of atoms is what we're trying to find. We still have to sort and strategize. So we've got a number of years. We've got this relationship and this relationship. Usually, the number that has just the plain old unit is going to be where you're going to start. So we're going to start with years. And then we're going to go from years. We have a relationship between years and seconds. We can go from years to seconds. And then we have this rate. Come on, pointer, there we go. Atoms to seconds, so we go from seconds to atoms. So, years, and then we're going to go to seconds, and then we're going to go to atoms. Now, some of you can just look at this problem and know what you need to multiply or divide, and others can't. That's fine. So we're going to put the units in here so they cancel out. But instead of using our calculators, we're going to do an order of magnitude estimation. So the number of years was 1.4 times 10 to the 10th years. Rounding to an order of magnitude, what's that going to be? 10 to the 10. And 1 year is 3.2 times 10 to the 7 seconds. What do we round this off to? 10 to the 7. So 10 to the 7 seconds is 1 year. 10 atoms per second. Well, that's already rounded for us, right? So 10 atoms per second. Now we have 10 to the 10th times 10 to the 7th times 10. 10 is also the same as 10 to the first power. When you're multiplying powers of 10, you just add up the exponents. So 10 plus 7 plus 1, this is going to be 10 to the 18th. And that's the answer, atoms. I don't intend to specifically test you on order of magnitude estimations, but it's in your book, and I think it's useful to know how to do that. Any questions? Some problems involve an equation, and you can't use dimensional analysis. You have to use the equation. Usually what happens then is however many variables there are in the equation, they'll give you values, or you'll be able to find values for all of them except one, and then you just have to rearrange and solve. So I'm not going to do those examples either.